Good morning and welcome to today's technical section. I'm by name Sifas Jalai and a proud member of the Sky Technologies. And I welcome you all to today's technical section. I'll be speaking to us today on a topic captioned Advances in UAV Avionics, System Architecture, Classification, and Integration. I take the topic again. Advances in UAV Avionics System Architecture, Classification, and Integration. Now, first of all, I would like to speak about the avionics in general. Um, Avionics comes from two words, aviation and also electronics. So two words come together to give birth to what we call avionics, which is aviation and electronics. Hence, the avionics is a portmanteau of the word aviation and electronics. All right. Now from the screen, I have a avionics of the rotary wing UAV. The avionics of the rotary wing UAV. And now we have different section of the drone system with their avionics being displayed. Look at them. We have the ESCs, we have the antenna, we have the motors themselves, we have the FC's flight controller, the control board, the autopilot, the compass, the global positioning system module, which is GPS. There's several of them, and they are all classified into different, they're classified into different categories. Every of these avionics systems have a place they belong to, every one of them. Now, by introduction, unmanned vehicles are increasingly used in diverse fields. First, the use of drones cut across different fields of endeavor. Talk about agriculture, talk about in the delivery, talk about surveillance, talk about in the military application, civil application, in operations. Drones application cut across different fields of human endeavor. So with this application also comes the need for advances of what avionics systems. The avionics system that will be used on a drone, which is used for agriculture, definitely will differ from the avionics system that will be used on a drone that is meant for surveillance. Some of the electronic systems, some of the electronic system, that's avionics system now, will be it definitely differs. Now, permit me to say this to make clear this statement that for the purpose of this class, I'm going to be using avionics and electronics interchangeably. Avionics is the right term to use. Yes, avionics is the right term to use as per the the register word for this. But permit me to use the word electronics interchangeably with avionics. So, as like I said earlier, that different application of drones most time requires different advances in terms of their avionics systems that will put on board. The avionics system that will be on board a drone that will be used for probably, let's say, for surveillance differs from the one that will be on board for agricultural purpose. So, depending on the complexity or how robust a mission is, that determines how robust or how complex also the avionics system too will be. Just for example, let's look at our PC. Our laptops comes in different categories, in different grades. The laptop you can use for computing, high computational works, you can't use for works that probably need for probably administrative works. Even though you can still use the systems that are of high computation for those that are for works that have to do with administrative work. But you can't, in most cases, you can't use systems that are majorly used for administrative purpose for those ones that are majorly for computational purpose, because it requires a lot of capability, and in most cases, systems that are majorly used for administrative purpose are not of high capacity compared to those ones that are used for high computational purpose. In that regard, developers said that avionics systems are critical for navigation. That is, the avionics system of every drone, regardless of whatever mission they are meant for, these avionics systems are critical for navigation, they are critical for communication, and also for mission success. Also, we have unmanned aerial vehicles, commonly known as drones, have evolved from rudimentary radio-controlled aircraft, yes, to sophisticated autonomous systems. If you no longer want to use controlled, radio control for controlling your drone can go autonomous now. That is, it can automatically fly itself without any inputs from any human. So your drone can fly either with human inputs partially or completely, and also it can fly by itself without any human input. So autonomous system. The avionics onboard systems are central to enabling safe, efficient, and intelligent flight operations. So this avionics onboard enables it to have, an intelligent flight operations. So without, of course, there's a definition I used to give that UAVs, just as the name goes, unmanned aerial vehicles, are aircraft without human on board and uses what? Radio systems or radio, yes, radio systems for what? For flights. Yeah. So the onboard electronics on them allows for their autonomous systems. This system manages everything from navigation and communication to energy management and threat mitigation. So the avionics systems on board helps to manage everything on it, from navigation, in moving around, in knowing the path to follow, in communication, probably relaying back to the control station, and even probably between drone to drone, just as we have aircraft communicating to aircraft communicating to ground stations. So also we have drones being able to communicate with other drones communicating with what? With the operator, probably the pilot. And likewise, also being able to manage the energy on it, and also threat mitigation. So the avionics component helps to, enable all these things are in place, because in this present modern age we are, since drones are capable of doing different things now, there are a lot of threats to it, especially as it pertains to military applications. There are lots of threats that comes to drone usage. Now, definition. So the system of an unmanned aerial vehicle or drone are the critical electronic component found on board that regulates, navigates, and controls UAV travel while ensuring public safety. So this is to tell us that what the avionics components cut across. We don't need to look at avionics component as just mere electronic components, like mere electronics, just like probably we have on our PC, on our phones, on our TVs, on our electronics components, at homes. or electronic appliances at home, we need to look at avionics system in that manner, because the avionics system on board UAVs allows for every other systems of it to function optimally. So it helps to what regulates, it helps to navigate, it helps to control UAV travel while ensuring public safety. So every avionics, the truth is there is no part of the systems of the drone you look at that doesn't have avionics components on board it. Almost no part of it you're going to look at that has no electronic components or avionics components attached to it. So the avionics system allows for regulation, for navigation, control of UAV travel. That is, in terms of the path planning, the mission planning, with once you plan your mission and you want to execute, the avionics system still will be what you're going to rely on to help in carrying out or accomplishing the task. So what are the historical evolution of the UAV avionics? Now, the truth is, to go back history line, the avionics system can be traced back to World War One, where electrons relied on mechanical initial systems. The question is, what are mechanical initial systems? You know, it's a system that refers to the component that measure UAV's motion. You know, UAV's motion, orientation, and acceleration. Okay. After that, again, a UAV avionics mechanical initial systems refers to the components that measure the UAV's motion, orientation, and acceleration. And this contain majorly of IMU, you know. So the avionics systems dating back to World War One make use of mechanical initial systems. The interwar period saw the emergence of radio-controlled aircrafts, laying the foundation for modern avionics. So after World War One, the wars that happened in between, probably the wars that happened between those periods, led to the emergence of radio-controlled aircraft, laying the foundation for modern avionics. And also over the decades, there have been iterative advancements that have led to highly integrated multifunctional avionics capable of supporting complex missions. Yeah, like I earlier stated, that the more robust a mission is, the more complex a mission is, also the more advanced the avionics system that will be on board it. Now, you look at the likes of Berata, look at the likes of the military grade drones. You can't compare the avionics systems to the likes of Mavics, maybe the Mavic drones, or look at drones that are basically used for aerial photography. You can't compare. Their avionics system differs. Hence, these things didn't just come by. They were iterative methods or iterative advancement that led to these things. From one advancement to another, from one level to another. So the iterative advancement have led to highly integrated, multifunctional avionics capable of supporting complex missions in both civilian and military domains. Yes. And we also have our military missions, civilian missions that are very complex too. They are very robust. And with this comes also with words, advancement in the avionics that need to be placed on the drone. So this is just a breakdown of what I initially stated, that we have mechanical initial systems in World War One. By World War II, we already have what radio controlled aircrafts. And after all that, in the present day era, we have fully autonomous and AI integrated systems. Yes, in this present day now, we have AI systems being integrated on board our UAVs. Yeah, AI systems being integrated on top of our UAVs. And likewise, drones autonomously flying by themselves. Not just even within the region of the Earth alone. We have drones that flies as close as the stratosphere level. That's when we talk about what high altitude pseudo satellites, like drones acting as satellites. You know, that's what we refer to as HAP system, HAPS, high altitude pseudo satellites. Right. Then we have avionics system architecture. Yes. So what are avionics system architecture? It refers to the overall design and structure of the avionics systems on board and unmanned aerial vehicles. I take that again. It says it refers to the overall design and structure of the avionics system on board and unmanned aerial vehicles, which encompasses the organization, the integration, and interaction of various avionics components and subsystems. Subsystems like what? Flight control systems, navigation systems, communication system, our sensors and payloads, even power and energy systems, the navigation systems, the perception systems, you know, all these things are like subsystems in which are encompassed in the UAV avionics architecture. So, UAV avionics include flight control surfaces, sensors, just like I mentioned. Uh, so this component must operate harmoniously for mission success. All these systems must together what? Interact together. They must together. They must interact together in order to have the mission successful. And let's look at the. Don't forget, we're talking about what advanced UAV avionics systems, architecture, classification, and integration. And now, let's look at the advanced avionics system architecture for this. Of course, we have terms. I mean, we have architectural systems initially, yes. But now we are looking at what? The advanced architecture systems that are presently used on our UAV. Don't forget, I said the more advanced or the more complex your mission is, then the more advanced your avionics system too will be. So we have avionics system architecture, okay, that are in existence, but we also have those ones that are advanced. So the advanced avionics system architecture include the modular architecture and also the layered architecture, modular architecture and the layered architecture. Okay, so the modular refers to a design approach where a system is made up of separate, interchangeable parts, that is modules, that can be easily added, removed, or swapped out without affecting the rest of the system. All right, now, couple of, I think earlier this year, when the project we're working on here in our facility started, and we needed to make selection for some of our the parts. You know, I remember that while we were trying to make selection, some of the system come as a whole. Like when you click on a particular picture, you see that okay, there are different components. So it's either if you like, you decide to get a component, or probably you get the whole components together, the whole system together. So the fact that you can detach a system out of it and still be able to use it to achieve at least a purpose. Such components are referred to as modular architecture. So it refers to a design approach where a system is made up of separate interchangeable modules that can be easily added, removed, or swapped out without affecting the rest of the system. And we have the layered architecture. It refers to design approach where a system is organized into different levels. that work together. So different levels that work together, each with its own specific job or function. Each with its own specific job or function. All right. So uh, the modular architecture now in full. So modular architecture in UAV units include but not limited to one, the flight control systems. So one of the modular architecture in UAV units include the modular flight control system. This is interchangeable modules for different flight control algorithms or pilot systems or navigating system. All right. So we can have interchangeable modules for different flight control algorithms or pilot systems or navigation system. Modular payload system. Several payloads for different sensors, cameras, or communication systems. So we have different payloads that can be swapped. You know, the fact that, for example, BS Chooks, when it was designed to be able to make use of swappable payloads. You know, so probably you can have a payload that is meant for uh, medical delivery, okay? And at the same time, you can swap to have a payload that's meant for aerial photography, okay? So you can have suitable payload modules for different sensors, all right? Cameras or communication systems. Okay, for the layered architecture in UV Linux, they include, but are not limited to, application layer, which are mission-specific applications, such as navigation or communication. Of course, navigation or communication systems are mission-specific. Also, we have navigation. Okay, just like I said, navigation layer. The navigation layer includes GPS and other sensors, which provide location and navigation data to the flight control layer. All right, then what are the classification of avionics systems? What are the classification of avionics systems? Avionics systems are classified into communication, identification, energy storage, perception and navigation, path planning and control, data buses. And from the diagram and from the picture, you get to see different avionics systems. Yeah. All right. So the classification of the avionics systems, we have like I said, the communication, the identification, the energy, the sensors, navigation and control, electronic warfare, certification, and I mean all these systems made up of our avionics systems. All these are the classes of our avionics systems, and okay, so the classification of avionics systems, talking about the identification systems. Now, the truth is, a lot of advances have happened to all of these avionics systems. The fact that all these systems have been in existence in this modern era, a lot of advances have happened to them along the line. For example, now we have drone. You look at the swarm systems, swarm drone we have in this present day, or drones that are used for public display, whereby you have them being used to draw images. I mean, you can have like over 100 drones being used to draw an image, you know, just like night sky kind of thing. So, like I said, a lot of advances have happened to them. For example, we have the ARINC, all right, So still on the classification of avionics system, all these slides, I mean, talk about the advances that have happened to them, the both in the energy storage, all the advances that have happened to every classification or all systems that pose multiplication of avionics system in the energy storage, in the communication system, in the navigation system, and then also even perception and navigation. The GPS we used to have back in the days are not what we used to have in this present time. Advances have happened to that. Likewise, in our IMU, inertial measurement units, the LiDAR, the vision sensors, a lot of them, advances have happened to all of them altogether. So major advances in the UAV viewing system include transition from isolated subsystem to modular layered architectures that integrate flight control navigation, just like I've stated that the advanced architecture systems of UAV avionics include modular and what's layered. It says we've been able to transition from isolated subsystems into modular layered architectures that integrate flight controls, navigation, communication, energy, and perception systems. In most cases, you're able to see some of these things just on a singular board. For example, a board like this, in this, as you can see in this picture, something like this, or something like this. You can see some of them on a singular board like this. All right. So, in conclusion, I would say UAV avionics are the hearts of drone innovation. As mission grew in complexity, the integration of advanced, secure, and efficient avionics system will be pivotal in shaping the future of aerial robotics. Okay, so the avionics system are the heart of drone innovation because there's nothing we're going to do today that doesn't still have to do with the avionics on board the drone. Okay, so the avionics system are very pivotal in shaping the future of drone itself in every area of human endeavor, most especially as pertains to aerial robotics. And also, UAV avionics are rapidly evolving to support complex missions. Yes, the more difficult, the more complex, the more robust a mission is, the more advances these avionics that need to be used. Just as we have in the military missions. Military missions keeps getting complex every now and then. Likewise, in the civilian applications too, innovations keep happening. Hence, for these, we need to have advanced avionics system. So integration of advanced technology is key to future UAV capabilities. Integration of advanced technology is key to future UAV capabilities. So if ability to integrate the advances in technology is what UAV is what will determine how capable UAV will be in the future when we are able to integrate technologies, the advance in human technology, if we're able to integrate them, find a way of how they can be applied to UAV, just like we have in AI technologies now, AI systems. We're able to apply AI technology into UAV, and hence we have drone being able to function, being able to perform tasks that it couldn't before. And this brings us to the end of the uh, technical section. Thanks all for listening. Should in case you have questions,